Time for another draftphysics.com video presentation. So the Ian Gosling has finally done the correct experiment, and so great. It's not done perfectly, but it's it's getting close enough. Where there can't be too much to complain about if just fix a couple of the imperfections. So we'll play some of this. So we finally have the half mass at twice the distance. Now, as I stated in the previous video, we know the lever's consuming some of the energy, so the idea would be is to try to maximize the distances to create no reflection. So he's already demonstrated that you can make the mass go all the way straight through if you make the weight on the other side lighter and lighter by putting it closer to the fulcrum. And so that's all it needs to be adjusted for. You have to account for the fact that the lever is consuming some of the energy, so you can't do a strict 2-to-1. You have to change the R, okay, to adjust it to the amount of energy that you have lost. But anyway.
Here, Gary's one for you. This side time, the incoming mass is going to be this side, just the way it's arranged. So this is the one mass at half distance from the fulcrum, and the outgoing is the half mass at 2 distances from the fulcrum. Let's see what happens.
So simply put, because we know we lost at least 10%, you'd have to move that in 10%. So it has to be 10% in closer to prevent any reflection. So that's the key thing to look for. Will this reflect? Reflecting means that it's too heavy. So we'll see.
Here. Get that lever right.
So obviously some reflection. All right. And obviously this didn't leave very straight, which is not perfect. But it clearly does go further. All right. And what we have to know is how long are the strings. So if you know how long the strings are, you can calculate how high up it's going in gravity and how much the distance matters. So just a couple of inches makes a huge difference when you're going up the circle. So as you go up, this distance gets much shorter for the amount of gravity you're overcoming. The amount of time you're in the gravity. Alright, so so that's all you can really say is it's further. We just don't know the numbers. But the point would be is that there is a point where if you have 0 reflection here and 0 going through, if you have all the energy out of this object, the logic says it's only 2 places it can be, in the lever or in the weight. It can't be anywhere else. So those are your 2 choices. So it does.
The half mass seems to go.
It clearly goes over the board. Okay, so it's going up into gravity.
Further now, as I suppose you would expect, would you? Pushing less weight. We can't measure the speed of.
So it went over the board. Well, like I said, you don't have to. You can measure it by the distance. So, but yeah, there's ways you could do it. You just have to do it. I can't do it on the video because the video is not high enough quality, and the sounds aren't really perfectly. There is no sound, okay, for it going back. But you can just measure the arc of the swing of the pendulum, frankly, and that will tell you what velocity it was going. So that's doable. But yeah, so far, okay, yeah, it's indecisive in this form. But like I said, if you just provide the length of the distance between where they're, how far the center of their rotation is. Okay, so wherever the staples are to the object, that distance to the center of its mass.
Of course, which would be nice. It's been the problem with all these experiments, isn't it? If only we could measure the velocity.
Alright, so watch it once more. So, the bounce isn't significant. So I got to say that's, but it's definitely there. It definitely went back. It didn't go forward. So you need to move it in a little bit. And there'll be a point where this doesn't move. It stops. And then all the energy has to be in the lever or it has to be in the object, frankly. There's really no other place for it to be. I mean, you can't really argue about the fulcrum absorbing different amounts of energy. I don't think you can argue that.
Don't know. What happens if we would do this as the incoming?
Well, that's a waste of time. Okay, so, obviously it won't work. Light things into heavy things don't work. Reflection. Well, we'll just show it. Oh, yeah, it went through because this is much lighter. Right, you made this half the mass. And yeah, so that is it. That's not a totally insignificant experiment. It should go half the speed. Yeah, so maybe that is worth seeing again, frankly. Let's do that again.
If only we could measure the velocity.
Alright, so that's the heavy one in.
Don't know.
So the prediction would be here. So you got a light object hitting the heavy object further in, which means it weighs half as much from this thing's perspective. So they should weigh the same in theory. And the idea would be if this is going twice the velocity, this would go half that velocity. That's what my prediction would be, because that would conserve the momentum. So if you're going to conserve the momentum, the half as light object should travel twice as far as the heavy object.
What happens if we would do this as the incoming?
I should have thought of that. Yes, because it is easier to see anyway. So we have the incoming that went all the way to the board. And the lever does bend quite a bit. You can see quite a bit of bend there, unfortunately. That's unfortunate. Because this is, well, it's technically the same weight. So it just is a lot more bending than I thought you'd have. Alright, so, and now it's pushing it. And so it goes about halfway, indicating it has half the velocity. So it's close to halfway.
Come in.
Look at it real time. It's about halfway.
I've done a few different configurations, but what help it is, I don't know.
This is what you're supposed to do. This is help. This is exactly what you're supposed to do, is the experiment and then try adjusting it a little bit. So let's see if this goes all the way through, then we'll know it's not getting all of the energy into the object. So see what this end does this time. You can see this, right? I didn't screw something up. Yeah. Alright. So let's see if it bounces or goes through. Okay, there's the hit by by the bad frame. So it does seem to keep going through. So it's lost, it's not quite transferring the energy, because it has gone further than the bottom. So it's obviously not gotten rid of all its energy, but it's still in contact. So that's about it. That's about this is liberated barely. But clearly that's almost half the distance. Now it should be a little further than half, because this is the easy part, right? Going the up and down is the hard part. So going sideways is the easy part. So technically, for it to be twice or half the velocity, it should have been better than that. But again, we are losing to the lever, and we're losing to the fact that it's not really in good contact with the lever. Once the lever starts turning, the object's sliding across the lever. And so it's, it is a way of losing energy, unfortunately. And clearly this went way past neutral. So again, it's sensing it as being, again, you have to make this heavier in this case by moving it out a little bit. Or you have to move this in a little bit. You have to make it lighter. No, you have to make it heavier. You have to move it out a little bit. So you got to move the heavy mass out or the light mass in. So if you move the light mass in, it gets... no, he's got to move it out. Alright. Well, whatever. You should be able to figure that part out. Because you want this to stop after it hits the lever. But that just might be part of the problem. Just might be the contact points aren't quite good enough. So it might be better to improve the surface that you're hitting here by putting a little plate in front of the lever, you know, to get rid of the convolutions in the surface and try to make it a more even contact. Maybe that would help. But see if it's one more. Okay, it's going back to the old demonstration. Okay. Alright, so pretty inconclusive one way or the other. I mean, that certainly could be 1.3, 1.33, but you're still getting the reflection, which is just an obvious, that's energy that you didn't get into the other object. So anytime you have a reflection, you want to try to get rid of that, and the easiest way to get rid of it is just make the object lighter. So just move it in a little bit, one little 10%, move it in 10%. And see what kind of results you get. So anyway, good. Finally, getting somewhere. So, enough said, frankly. Yeah, I think that's enough. Yeah, I'm just, you know, there really isn't anything to lose the energy to except the lever. So you could argue if the lever's immovable because you put a giant object on one side, then you're going to get a pretty substantial reflection. But you could argue that some energy gets into the lever because it is wood. For frankly, you can't be sure that this is where the fulcrum being very solid has to be part of the recognition that the fulcrum can't be allowed to move at all. I mean, I didn't really watch the fulcrum, but I suppose that's something to do.
Don't know. What happens if we would do this as the incoming?
Alright, so let's see. Yeah, you can't tell. So anyway, we'll see. See how it progresses. So, yeah, you do need to give us the length of the pendulum. Then we can figure out the distance. Somebody can figure it out. I suppose I can figure it out. Even if I have to draw it, I should be able to figure out how high you're going per distance. And that'll tell you how much gravity consumed, how much work you did against gravity, how much motion you did against gravity. Alright. So, till the next time and such, I think that's enough of a video. So, good.